Okay, Zeynep.
Okay. Hi everyone, I'm Zeynep. I'm recently graduated from PhD, and this summer I had the opportunity to work with Demircan. Demircan is a senior year physics student at Boğaziçi University, and he's also doing double major in mathematics. So during this summer, he was very busy actually. He was a research intern student at Kahve Lab on Kandilli Observatory campus, which is a particle detector lab. He is also building currently an automatic water system for potatoes that he wants to grow at home. Meanwhile, he was taking courses during the summer school, and this fall he is planning on applying to graduate programs abroad. Even though his interests lie in the intersection of physics, mathematics, and engineering, he says that he's a physicist by heart. And this summer we reviewed some probabilistic concepts with him and then looked some machine learning applications. And stage is yours, Demircan.
Thank you, hocam. First of all, I want to thank to all organizers for their volunteering work and to all mentors, and especially, by the way, can you hear me well? The people of the Zoom, okay. And he attends from America. In America, it is 4 in the morning right now. Thank you for your efforts. Today I'm going to talk about probability theory and its one application. But before I start, I want to point out that the logo of Sabancı University, here dots are not aligned, and it is not a typo, as you can see from here. Yes. It is not possible to even give an introduction to probability theory in 20 minutes. But the thing I studied was the introduction to probability theory because I wanted to learn concretely probability. Today I'm going to assume that your information about probability comes from your high school education. So I hope that I'm going to be understandable throughout my whole presentation. We are going to start with the probability space. And when I define some things, I tend to give examples to make them more understandable. And then we are going to talk about conditional probability and independence of events, variance and covariance. At the end of my presentation, I'm going to give one application of probability theory into machine learning. The examples are not that complicated, by the way. They are just interesting for me, and I wanted to share with you. To be able to concretely talk about probability, we need to define probability space, which has 3 components. The first is the sample space. We are going to assume that there is an abstract experiment, and this experiment outputs some random output. The set of all those outputs are called the samples. Is called the sample space. And the second component of probability space is the event space. It is a collection of subsets of omega. By the way, sample space is denoted by omega. The conditions are omega being a subset, an element of event space, and if A is an element of event space, also the complement is. And the third third property is the it is closed under countable union. And our last, by the way, those conditions come from measure theory, I am told. And the third component of some probability space is probability measure. It satisfies the axioms of probability, which are non-negativity, normalization, and countable additivity. Now let's give an example to make those ideas concrete. Assume that our experiment is throwing a 4-sided dice. Now the possible outcomes are 1, 2, 3, and 4. So our sample space is given as such. And those are example events. For example, this means the outcome is 3. This means the outcome is either 1 or 3, etc. So an event space construction could be like that. Only omega and empty set. It satisfies all the axioms I said. The second can be the outcome being either one or not one. And we said that it also need to have the omega and the complement of omega. So this is a valid event space example. And throughout the slides, we are going to assume that the event space actually the power set of omega, all possible subsets of omega. Now, let's give the definition of conditional probability. This is read as probability of A given B, and its definition is like that. This basically, the intuition behind this definition is that you restrict yourself into B, and you give the events that are outside, you give the zero probability to the events that are outside of the B, and you take the probability of events that are both in A and B, and you rescale them by probability of B, so that now again you satisfy the sum of all probabilities has to be one condition. And the definition of independent is that the events A and B are called independent if their probability satisfy this law. This is not that intuitive, so let's play with the definition a little bit. Let's put the independent definition to the conditional definition. We notice that if A and B are independent and the probability of B is not zero, then probability of A given B is probability of A. It is intuitive. It says, I don't care whether B occurred or not. The probability of A is probability of A. Yes. Now let's give an example that I found interesting. Now let's assume that our omega is defined like that, and the events are defined like those, and the probability of the outcomes are given like that. Now we see that A and B are not intersecting. In mathematical terms, they are mutually exclusive. Can we say they are independent? By the definition I give, it turns out no, because their intersection is empty set. Probability of it is zero. Probability of A is calculated by adding the probability of 0 and 1, which is 1/3, and similarly for probability of B. And we see that 0 is not equal to 2/9. So they are not independent, even though they are not intersecting. We see that A and C are intersecting. They are not mutually exclusive. Are they independent? Yes. If you do the math, you are going to find that they are indeed independent. This is actually very cool because the concept of independence is now concrete. Now you can mathematically look at the coin toss game as defined probabilities, and you will see the first coin being heads is independent of the second coin being heads. You mathematically now concretely can define and work on that. Or next definition is going to be the expectation or the mean value of something. Mean value of an experiment is calculated by multiplying possible outcomes with corresponding probabilities and summing for all of the outcomes. And now we know the definition of expectation. We can look at the definition of variance. Definition of variance is given like that. You again sum something. What do you sum? You take the difference between the output and the mean, and you take the square of it, and you calculate for all of the outputs. I was like, of course, in physics, we use those definitions, but I was like, why do we take the square of it? why do you sum the squares? I mean, we can take the absolute value of the difference, maybe. They were saying if you didn't take anything, you wouldn't, sorry, let me rephrase. If you didn't take squares and you take just the mean value, you get 0. It gives no information. So you take square of it. But this was not enough for me. And when I looked at more into that, I found two reasons to define the variance, how various your data from mean is defined like that. One is because in general we work with Euclidean space, and this distances in Euclidean space is defined by squares. So when you sum them, you get something familiar. And also, by this definition, Gaussians work well. Your calculations become much simpler. And now we can look at the definition of covariance. We saw that variance of x means how variate x from its mean. It's a measure of it. And covariance between x and y is defined like that. Actually, yes, she gave a definition of correlation in her slides, Gizem Ezgi. Here we look at the covariance part of the correlation definitions. It is again a sum over those two things. And the intuition behind of covariance is that you sum those two those things. If x exceeds its mean, this is a positive value. If y also exceeds its mean, this is a positive value. If they both together exceed their mean, you sum positive. If both subseeds their means, you again sum positive. So at the end of the day, if you calculate covariance to be positive, you say that, okay, they tend to exceed or subseed together. They act together. And vice versa. If one exceeds and one subseeds, then you get a negative covariance. And if the covariance is 0, we say that x and y are uncorrelated. Those are some examples. Those graphs are examples of correlation. Correlation is basically normalized covariance. Here we see that if the correlation is 1, they tend to, without any noise, they tend to increase together. But this cannot catch the slope of your tendency. And if their correlation is not 1, you see that they kind of act together, but it is noisy. And unfortunately, if you with this definition, we can't catch the linear behavior. We only catch the linear behavior of our data. We don't catch nonlinear behavior like those. For example, when you look at this example, you see that as x increases, y both increases and decreases. You have some kind of relationship between them, but this definition doesn't catch because as much as it increases, it decreases too. So at the end of the day, you get 0. Yes. And by playing the definition, multiplying these two brackets and using the linearity of expectations, or it was the fancy name, the properties of summation, you end up a different formula, equivalent formula for covariance of x and y. Now, the interesting example of this topic is that, is it possible for two random variables to be dependent but uncorrelated? The answer is yes, but since I do not have time, I'm not giving you the example here. There is a link, you can click on it from my presentation. But the core of the counterexample is that probably this being 0, which means those being equal, doesn't imply that probability of x given y is equal to probability of x. Yes, this slide has a blue background. And this is a regular slide. Now, we are changing our perspective. From now on, I'm going to talk about one application of the probability concept in machine learning. But I just want to, as I said, I want to be understood by everyone. I'm very briefly going to talk about what is machine learning. We have a machine and we want it to do some task for us. For example, when we give it a picture, we want it to decide whether it is a picture of a cat or a dog. Or, for example, if you a doctor, you can give the X-ray of a patient, and you can say whether this patient has a cancer or not. Now, how do we do that? Machines learn like children. You give them lots of examples, inputs and the expected outputs, and by tuning some parameters, the machines get a function which satisfies the properties we want. If it is a cat, output, I don't know, maybe 1. If it is a dog, output 0. But this is actually magic, because in the point of view of machines, a picture is just an array of numbers. And we want from machine to make sense of those numbers to whether a dog exists in a picture or not. And for example, a 4K image has 8.3 million pixels, and each pixel has 3 red, green, blue values. It is lots of numbers to calculate and work with. So our machine learning models tend to be very big and complicated. We want to overcome this issue. We want to decrease the size of our inputs. This is actually called dimensionality reduction. We reduce the dimensions of our input. This is just an example of one example is computational efficiency, but there are other reasons too. Another reason could be visualization. I am going to show you a visualization example. So we are going to see this. Another reason is curse of dimensionality. Basically, as your input dimension increases, your machine tends to learn wrong connections between the features. And another benefit is feature interpretation and noise reduction. I'm out of time. I need to be faster. How do we do this dimensionality reduction? One technique is called principal component analysis. Let's look at this graph. What is this graph? In this graph, every point corresponds to a data. So each data has 2 components, and we want to from 2 components to go 1 component. How do we do that? We put 2 directions, and we take the restriction of our data into 1 direction. And one need to notice our data is scattered along V1 direction. So when we take our data into our V1 direction, they are nicely separated from each other, and both they have 1 numbers, which is very good. But if we did the image on the V2 direction, they would clump together, so it will be hard to separate them. So we need to cleverly do our apply our technique. Here we apply our technique. We have flower data. In our data, every data point has 2 numbers associated with them, and we want to, by looking at these numbers, to decide what is the species of our flower, and sepal length, petal width, and the others. After principal component analysis, I have a 2-dimensional space, 2 dimensions for each my data point. If I plot them, I see that they are separated from each other quite well. So or dimension reduction is good, is doing a good job. Now, how do we separate the flower species from each other? We are going to put Gaussians on the means of our data. For example, we are going to put a Gaussian on the mean value of red. I'm not going to say the scientific name of species, red species. We are going to put a Gaussian here, a Gaussian here, a Gaussian here. And for any given point, we are going to look at those three Gaussians. Which one is higher? We are going to say, okay, this point should correspond to this type of flower. Here we also assume that the shape of the Gaussians is the same. So the only difference between two Gaussians is going to be this exponential part. This exponential part, if you do the algebra, you are going to notice that when you compare those exponentials, they are linear discriminators. They are the difference between them is linear. As I said, I applied this technique, and you see the decision boundaries are linear. And since I am out of time, I think it is a good time to stop here. After applying this technique, I get a 97% success rate, which is good actually. I want to thank to Dr. Bobat Nazar from Boston University. I followed his lectures. You can scan this QR code or click on this link to get his lecture series. There are exams, videos, lecture notes, lots of material. And I used also these artificial intelligence models to prepare my presentation. And I also put the link of the Python code that I used to apply the probabilistic techniques on my data. Thank you for listening. Any questions?